Now we're going to go ahead and talk about two examples of subspaces. And so the idea is if we have a matrix A, there are going to be two special subspaces related to that. The first one, the one that's easier to understand, is called the null space of A. And I will usually write this as capital N parentheses A just to have a shorthand for it. And what this is the set of all solutions to the equation AX equal to 0. So basically you take your matrix A, you set up a system of equations, set it equal to 0, and you look for all possible solutions of that. And if that's the case, then you have the null space of A. The other one is called the column space of A, and this is a little bit harder to see here. And the notation your book uses for that is COL of A. This is the set of all linear combinations of columns of A. Now, what do I mean by that? Let's take an example here, A, and let's make it 1, 2, 3, 4, 5, 6. So the idea is the null space, this is going to be the set of all solutions to the system of equations here. Let's a little room here. There are three variables, x, y, z. All right, so you set the system equation, you solve it, and that gives you your null space. On the other hand, the column space, what that is, these are all possible combinations of the columns here, 1, 4, 2, 5, and 3, 6. So that means you're going to take some sort of constant times 1, 4, plus some other constant times 2, 5, plus some third constant times 3, 6. And you're going to see what are all the possible answers you could get from this. And if you take all the possible answers, that's going to be called the column space. Now, trying to figure out exactly what these are can be pretty tricky. So we're going to simplify the problem a little bit, and instead of trying to find the null space and the column space, we want to find the basis. And so let's talk about what a basis is for a subspace. This is a set of vectors that is linearly independent and that spans the vector space. Now, what do we mean by span? What this means is that every vector in the subspace is equal to a linear combination like this. So if you can get every possible answer doing linear combinations like that, then it's called a spanning set. Let me give a quick example here. If you have the vector space R3, there is a basis for that would include three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the idea is if you were to check, those three vectors are linearly independent. And if you have any vector in R3, you can write it as a combination of those. So for example, if you have the vector A, B, C, just any random vector here, you can rewrite that as A times 1, 0, 0 plus B times 0, 1, 0. Oops. Plus C times 0, 0, 1. So that means that no matter what vector you have in R3, you can write it as a combination of those. You can also check that it's linearly independent using the methods from that earlier section. And so that means that's a basis. And so what's going to happen is we're going to learn, there's one procedure you're going to learn, and if you do the work, you're going to get both a basis for the null space and a basis for the column space. And so you can definitely expect on the test that I will ask you, find the basis of this null space and then find the basis of this column space. So let's go ahead and move on to see how that's done.